हाय डियर स्टूडेंट्स, अगर आप इन वीडियो लेक्चर्स का मैक्सिमम यूटिलाइजेशन करना चाहते हो तो आई थिंक आपको ये इंप्रूव सेशन डेफिनेटली फॉलो करना चाहिए और रिलीजियसली फॉलो करना चाहिए। इंप्रूव सेशन क्या है, इसका लिंक डिस्क्रिप्शन बॉक्स में है, तो जाओ उसको चेक करो। इसके अलावा अगर आप व्हाट्सएप ग्रुप ज्वाइन करना चाहते हो, और मुझे लगता है आपको करना भी चाहिए, तो आप क्या करो, हमारे वेबसाइट पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो या फिर इस व्हाट्सएप नंबर पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो, सो दैट हम आपको उसमें ऐड कर सके। चलो अब पढ़ना शुरू करते हैं।
Okay, hi, welcome back. This is a video regarding the basics of rotational motion, and here we'll talk about topics like what exactly is a rigid body and the concept of angular velocity and angular acceleration, and then we'll do the kinetic energy of a system in a pure rotational state and the rotation with constant alpha or constant angular acceleration. Okay, so rigid body is basically a 3D body. In general, a 3D body. It can be 2D body as well, for which for any two particles, particle P1 and particle P2, the relative positions or the distance between those particles is not going to change with respect to time. Okay, so if this guy is moving, going from point A to some point B, and suppose apart from the translating, this guy is also, this system is also rotating about a certain axis, suppose about this axis with angular velocity omega. So after some time it's going to look like this. Okay, somewhere here it's going to look like this, and this P1 might be somewhere here and P2 might be somewhere here. So although there will be a displacement or net displacement for those particles P1 and P2, the distance between P1 and P2 should not change. If that is the case, I can term that body as a rigid body. Okay, and now let's talk about the angular velocity. So suppose I have a point here, point P, and a fixed point here at point O. Okay, now suppose this P is having a velocity of V at a certain instant. Now let's talk about what is the angular velocity of P with respect to point O. So this P's angular velocity with respect to O, first of all what I'm going to do, I'm going to join the line OP. Okay, so this P might be having like some angle theta with this line joining, let's call it the radius line. Okay, and this is going to be V cos theta and this is going to be V sin theta. Now this V cos theta is the V parallel component and V sin theta is the V perpendicular component. Okay, if I ask what is the angular velocity of this point P about it O, it's basically the rate at which the this line joining OP travels. Okay, travels in a certain angular direction, so maybe clockwise or maybe anti-clockwise. So angular velocity in this scenario is basically defined as omega, and that is V perpendicular, that is V sin theta, and divided by this length r. Okay, so this angular velocity of this particle P with respect to O is V perpendicular divided by r. Now keep in mind, angular velocity is basically the angle traveled by the line OP, the line joining OP from the initial direction. So initial direction might be like this, and after some point this point P might be somewhere here. Okay, and the angular velocity is basically the rate at which this angle is going to change. Okay, and now keep in mind, if the body point O is here and point P is here, and if the point P is moving along this line OP, the angle that it makes with this initial direction is never going to change, that is always going to be 0. So to change the angle, like the line joining O and P, okay, so you need to have a perpendicular component of the velocity, and that basically goes inside the formula for the omega. Okay, now if this is V perpendicular by r, I can write that V sin theta divided by r, or in a cross product form I can write that r cross V divided by r mod square. Okay, so you'll see this formulation quite often, but in general you're going to see the scalar formulation, and scalar formulation is going to be just omega is equal to V perpendicular divided by r. Keep in mind, this r cross V is going to give also the direction, the vector form of the omega. Okay, so if I'm going to take the r cross V, this is my r, okay, and this is my V r cross V using right hand thumb rule, this is going to be outside of the plane. Okay, so if the body or if the point P is moving anti-clockwise, the omega is going to be out of the plane, and is going clockwise, it is going to be into the plane, because r cross v is going to be inside. Okay, so the only thing that you have to keep in mind is that omega is v perpendicular divided by r, and the vector formulation can be given by r cross v divided by r mod square. Okay, now what is angular acceleration? Angular acceleration is nothing but, in a vector form, this is nothing but the rate of change of angular velocity. Okay, and this angular velocity can also be written in terms of the angular displacement, that is d theta by dt. Okay, now kinetic energy in pure rotation. Suppose we have a system of particle, and for in that system there are n number of particles. Okay, and this whole system is rotating about this axis with a certain omega. Okay, now each particle is going to have some mass mi and a corresponding distance from the axis of rotation ri. Okay, so this is my ri, and this is my ri for this guy and then this guy. So I'm going to have multiple number of ri's, and I want to find the total moment, total kinetic energy of the system. Okay, so I know Ke of the system is basically summation of all Ki. Okay, and each particle is going to have like a certain speed. Okay, so for Ke of the ith particle is basically half into mi into vi square, where vi is the speed of the ith particle. Think about it, if this whole system is rotating about its axis o dash with respect to with some angular velocity omega, each particle is going to have a speed vi is going to be omega I into r, that you can see from this formulation. Okay, omega is v perpendicular divided by r, so there is nothing like a radial velocity or something. All those velocities are basically going to be perpendicular to the line joining the the point and the axis of rotation. So this v perpendicular is basically omega into r, and for each particle I'm going to take mi and omega I r ri square. Okay, now keep in mind omega I is same for like each particle of the system. Okay, so I can basically write half mi vi is going to be omega into ri square. Okay, now I'm going to sum for all ki, so that means Ke net is going to be summation of half mi omega ri square. Okay, now since omega is constant and 1 by 2 is also a constant, so I can take omega by 2 common, and the summation is going to be mi ri square. Okay, so if I have this term, I'm just going to multiply with omega and I'll get my answer. Now keep in mind this one mistake is vi square is going to correspond to omega square ri square, so this should be omega square, and this also be omega square. Now this term is known as the moment of inertia, and we're going to discuss about this in the in the future videos. So for the time being I can write Ke net of the system is equal to half I, where this whole term is I into omega square. Now keep in mind this is just for the kinetic energy of a purely rotating body. If the body is also translating, that in the center of mass of the system is also translating, you're not going to see just this formula. In that case the formula is going to change a little bit, and we'll see in the future videos. For the time being it will be sufficient to know that if the body is undergoing a pure translation motion, the kinetic energy of the system is basically half into I into omega square, and if I'm talking about a discrete particle system, that I is basically summation of mi into ri square. Okay, so let's move on to the last topic of this video, that is rotation with constant alpha. Okay, so let me get rid of this. Okay, so as we have seen in the case of kinematics, that if A is constant, we can derive several equations like V is equal to U plus AT and S is equal to UT plus half AT square, and then we have the scalar formulation V square is equal to U square plus 2AS. Okay, so that's similarly exactly using those formulation that omega is going to be d theta by dt and alpha is going to be d omega by dt, and if alpha is constant I can use the basically exact same integral derivation from the kinematics, and I'll get my those equation in rotational sense, and that is going to be omega is equal to omega naught plus alpha t, where omega naught is the initial angular velocity and omega is the any final velocity as a function of time. Okay, and I can write theta is equal to omega naught t plus half alpha t square, and then omega square is equal to omega naught plus 2 alpha theta. Okay, so these are the corresponding equations in the rotational sense, where the body is undergoing a constant alpha. Okay, so for the time being, this concludes the basics of rotational motion. In the next coming video, we'll do like the advanced topics like torque and angular momentum and the conservation of angular momentum, and then we'll move forward to rolling and then problem solving. Okay, in between we won't be deriving simple basic equations like parallel axis theorem and perpendicular axis theorem. We'll be focusing more on the problem solving aspect of it. Okay, so stay tuned. We'll see you in the next video. Thank you.